It's Paul with a script that is designed to explore what happens when you look at the central limit theorem, student t-distribution, and confidence intervals, but use real data instead of hypothetical distributions. So let's first look at the simplest situation. Suppose you have a case where you've drawn a sample from a population. You think you know the variance of that population, but you don't know the mean. And a standard case where this is believed is SAT scores. You can look at the College Board website, and they say in 2015 the standard deviation of SAT math scores was 120. So I'll store that in the variable sigma, and I'll load up our data set with SAT scores. This had both math scores and verbal scores. I'll pull the math scores out into a vector and compute the mean SAT math score, 613. Either this is phony data or it came from a mighty good high school. That's a pretty high average. We'll need the length of our sample too, a substantial sample, 285. And let's suppose that the statewide average score was 600. I don't think there's any state for which this is true, but at least it makes the computation interesting. And what we want to know is whether our school is significantly better. So here's a simple approach to the problem. The central limit theorem says that if we draw a sample of 285 from the population in the state, no matter whether or not the distribution of SAT scores is normal or not, the central limit theorem is going to kick in. We'll know that the mean will be 600. We'll know that the standard deviation will be sigma divided by the square root of the sample size, and because of the central limit theorem, the distribution will be normal. So we can actually plot the distribution of those scores. You see it on the right. It is the normal distribution with the statewide mean of 600 and a variance appropriate to our sample size of 285. We can show our mean on that, and it makes our school look pretty good, doesn't it? We can calculate, in fact, the probability that that normal distribution will lead to a number larger than our school's mean. It's around 3%. That's our p-value. Notice, we could have done this analysis even if we didn't have the raw data from the school. If we just were told the mean for our school is 613.4, we could reach this conclusion because we're assuming that the standard deviation quoted by the College Board applies also for our school. Here's a cute graphical trick. I can't remember where I found this, but it's a recipe for shading in the area to the right of the red line. What you do is generate a pair of vectors, x points and y points, that outline a polygon that you want to shade in. And after you've drawn your graph, you call the polygon function with the points you've generated and the color. And isn't that beautiful? You've shaded in the region surrounded by those points and the axes. Here's an equivalent way of doing the same analysis. You create a standardized variable, standardized because its distribution is standard normal. And back in the days where people didn't have computers, but instead they had big books of statistical tables, a table of the standard normal distribution and tables of student t-distributions for various numbers of degrees of freedom, this was the way to go. So what we do is we take our school's mean, the sample mean, minus the statewide mean, and we standardize it by dividing by sigma, the College Board's reported standard deviation, over the square root of our sample size. It's traditional to call this statistic z. Since it has a standard normal distribution, we can ask what's the probability that a standard normal random variable has a value greater than this. Greater than is achieved by setting lower dot tail equal to false, and we get the same p-value as before. This is how statistics was done back in prehistory when people had books of statistical tables rather than computers. Here's an alternative approach. Suppose we don't know the national sigma. We can still, if we have all the data from our school, use the sample standard deviation from our school. So let's do that. We compute the standard deviation from our school, and notice R does exactly what we want. It tries to estimate the standard deviation from the vector of data. This is interesting. The value came out to 80, which is leading me more and more to suspect that these data, which I carefully typed in, are not data from a real school at all. I think it's highly unlikely that a school with this large a sample would have a standard deviation so much smaller than the national average. Now we can generate the studentized version. We take the mean for our school, subtract off the statewide mean, but in the denominator, instead of using the national standard deviation, we use our sample standard deviation. And this studentized variable should have a distribution which is student t with 265 minus 1 degrees of freedom. We get the p-value. I first looked at that and I thought, oh, it's the same, and then I realized there's one more zero after the decimal point. This is smaller by a factor of 10, and the reason is we're using a significantly smaller variance now. If I plot the normal distribution using a standard deviation of 80 rather than 120, our school's mean score looks really good. Now, I used a student t-distribution, but I hope you figured out that when n is large, the student t-distribution is essentially the same as the normal distribution. So if I compute the p-value from the student t-distribution, I will get the same result, and I would get the same result if I'd gone ahead and used a normal distribution. The test that's automated, though, is the student t-test. Took me a while to figure out. What I'm trying to do is to assess the hypothesis that our school is better than the state average. That's why I looked only at the region to the right, and I have to put in alternative greater and say I'm testing the hypothesis that our school's score is greater than the statewide average. And if you look at what we got back, hypothesis is that the true mean for our school is greater than 600, and the p-value came out to be 0.002. The probability that our school is actually less than average is negligible. The confidence interval is quoted as 605 to infinity. That's because we're only interested in finding a number that we believe is very likely to be greater than the true mean. That's our 605. And this should be what I was computing in script 8M, only when I did it, I got 604 and change. The automated test gets 605 and change. I looked at the documentation, couldn't figure out what gives rise to the discrepancy. Okay, now let's try doing what student t was really designed to do. looking at what happens when you have smallish samples. So let's ask, if we had a sample of just 20 SAT scores from our school, how well could we estimate the school-wide mean SAT score? So now n is equal to 20, and the population now is the entire school. So from my scores, which are in the vector math, I compute my dot mu and my dot sigma. First, let's look at the distribution of means for a sample of 20. 20 isn't particularly large. On the other hand, the distribution of SAT scores is vaguely bell-shaped. It's got a big hump in the middle, and so the central limit theorem might reasonably apply for n as small as 20. We can check that. I draw samples of 20 without replacement, of course. We've got 285 to draw from. I plot a histogram of the result, and that's plausibly a normal distribution if we overlay the appropriate normal distribution function. The mean is the mean for our school, and the variance is the appropriate variance for our sample. That is, the standard deviation for the school gets divided by the square root of 20. We've got a pretty good fit. This is the one that generally works fairly well. The central limit theorem makes no assumption about the distribution of the population from which the samples are drawn. However, when we go a little further, we start to get into trouble. For a normal distribution, what we were able to prove is that if I take the sample variance, multiply by n minus 1, and divide by the true variance, the result should have a chi-squared distribution. So we can test this with real data now. Again, I'm sampling from math scores. I'm doing the same computation that I did in the other script when we sampled from a normal distribution. We look at the histogram and you say, yeah, it's got a long tail to the right. It looks kind of like what I've seen with chi-squared distributions. But if I overlay a graph of the chi-squared distribution, we're systematically off here, we're systematically off here, and things are not as good. The derivation of student t assumes that the distribution of n minus 1 times the sample variance over sigma squared is exactly chi-squared. So let's see what happens when we look at the distribution of the studentized variable. Again, I sample from the math scores, and again, I studentize. I subtract off the population mean and then divide by the standard deviation of my sample divided by the square root of the sample size. If everything came from a normal distribution, this quantity would have a student t distribution, and I was actually pleasantly surprised to see how close we came out. I think what this means is that if your underlying distribution has a nice smooth peak in the middle, you can use student t even though you know perfectly well the theory is valid only for a normal distribution. Let's see how we do with a confidence interval. So I'll set up a blank plot, do the usual where I draw a sample, compute the lower end and the upper end of the confidence interval, add 1 to my counter if the confidence interval succeeded in including the true mean. And as you can see, that red line intersects the confidence interval most of the time. And we hit it right on the nose, 95% of the time. And in this case, because 20 is a fairly large number, the quantiles for the student t-distribution are not that much larger than the quantiles for the standard normal distribution. Of course, R has this all automated. All I do is draw a sample of 20 from my vector of math scores I call t.test, and it says we're 95% certain that the true mean of SAT scores for this school lies in between 563.7405 and 627.2595. I trust about 2 digits of that at best. If I draw a different sample of 20 scores, I get a different confidence interval. But these confidence intervals do have the desired property. That is, 95% of the time, the confidence interval will include the true mean for the school. Now let's see what happens if the underlying distribution is not even remotely normal and our sample size is rather small. Looking through the scripts that were the data files that were already on the website, I found that one with the waiting time for a snack bar. So I read that in, and what we're interested in is the serving times. This, I believe, is serving times in minutes until someone gets their order handed to them. And when I look at a histogram of this, I see that the distribution of waiting times is distinctly skewed to the right. That means it's going to take larger samples for the central limit theorem to kick in. If I compute the mean waiting time and show it on the plot, it doesn't even agree with the most likely bin in the histogram. We could try to estimate the mean waiting time for this snack bar by looking at a sample of 10 customers and taking the average. So let's see what happens if we do that. First, let's look at the distribution of means for samples of size 10. This time I'm sampling from the vector of waiting times. Otherwise, everything is the same as what we were doing before. And when I look at the histogram, well, it looks kind of bell-shaped, but on looking at it, I can see there's a longer tail to the right than to the left. The skewness is less pronounced than before, but using a sample of 10 didn't get rid of it entirely. And when I overlay the distribution, the density function for the normal distribution, it's above the histogram on one side, it's below the histogram on the other side. Now let's check whether we get that chi-squared distribution that can be made from the sample variance. The derivation of that assumed an underlying normal distribution, and when we try it and look at the histogram, that isn't even remotely chi-squared. The chi-squared distribution has a much larger peak and much smaller tails. And that leads to suspicion that things are not going to work out very well when we studentize this variable. I'll do it nonetheless. Take the mean of wait times, subtract off the true mean, and then divide by the standard deviation of our sample over the square root of the sample size. If everything came from a normal distribution, this would have a student t-distribution with n-1 degrees of freedom, and you've seen from simulations in the other script that that works out more or less perfectly. I look at the histogram, that's not even remotely symmetric, is it? And when I overlay the density function for student t, it doesn't match particularly well. So let's see what happens if we just blindly go ahead and calculate a student t confidence interval. In this case, I'm going to compute how frequently we miss on the low end and how frequently we miss on the upper end. So I'll set up the standard blank plot and go through the usual routine of creating confidence intervals. I computed 1,000 of them, but only displayed 100. There's a vertical line at the true mean, and I think you can just by eyeballing this see there's a substantial number of times when the entire confidence interval lies to the left of the true mean. There seem to be many fewer cases where the entire confidence interval lies to the right. That's a consequence of our skewness. 93% of the time, the confidence interval included the true mean. Ordinarily, we get much closer to 0.95 than that, but the worst thing is this. The probability of missing on the lower end is only 0.002. That is, we're constructing a confidence interval that almost never lies entirely to the right of the true mean. On the other hand, we miss on the other side almost 7% of the time. That is, as you've seen from the graph, frequently the confidence interval that we calculate lies entirely to the right of the true mean. So this is a lousy confidence interval. However, this process can be automated. If you don't understand the rather strong mathematical assumptions that underlie the student t-distribution, you say, I know how to do this. I'll draw a sample. I will call t.test and say, I'm 95% confident that the true mean waiting time lies in between 0.3 and 0.67. And as you've seen, this confidence interval is not to be trusted. It's beyond the scope of Math 23C to explain what could be done about this, but in fact, Chihara and Hesterberg do a fairly good job of explaining this. There's a modern technique called bootstrapping, where you actually go back and look at your actual population in an attempt to generate sampling distributions appropriate for that population by resampling. And by using bootstrapping techniques, you can actually get fairly good confidence intervals in cases like this. But if you want to learn more about that, you'll have to take a real statistics course. I'm done.